about, let me write it better. Organic chemistry. Organic chemistry is the chemistry of carbon. Symbol C, atomic number 6. And the thing about atomic number 6 means that it's going to have, if we look at its electron distribution here, folks at home, you can find this in your textbook on the first page of, or second page maybe, of section 5.1, which is what you all will be reading tonight and doing concept check questions for. And so it has 6 protons, 6 electrons, and you will remember that means it's going to have 2 in its lower level and then 4 valence electrons. I'll spread these out. 1, 2, 3, 4. And so these are the first 4 electrons. Now, how many electrons does carbon need to be happy?
2, 4, 6,
8! Who do we appreciate? Carbon! 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 No. Only one of you is correct. Sebastian said 4, and a number of you said 4. 4 is correct. So we need a total of 8, folks. This is important, by the way. Don't forget you have a test on this basic type of chemistry on Wednesday. Organic chemistry is coming up. And remember, this atom needs 8 electrons total in order to be happy, which means 8 outer electrons total, which means it needs 4 more. Let's, I'll tell you what, I'll draw it.
Oh, so it doesn't fuse with other carbons?
What's that? Well, it can fuse with anything, and that's the thing about organic chemistry. Is you have this atom, and it needs to make 4 bonds. So here's the first level with 2, and this outer level has 4 electrons, and it needs to make 4 bonds, right? It needs to get 4 more electrons to be full. Quick review: chemistry, atoms bond with each other to get a full outer shell. In this particular level, it needs a total of 8. And so it'll form bonds. Like, for example, it could form a bond with 4 hydrogens, right? Because each hydrogen brings 1 electron to the mix. And so it would want to bond with 4 of those. Elements that are just between hydrogen and carbon are one large class of molecules called hydrocarbons, named hydrocarbons because they just have hydrogen and carbon. And this is the simplest one. What would be the formula for this? If I was to write the formula, if I were to write the molecular formula for this, what would it say? Part of your review. Say what?
CH4.
CH4 says Mr. Rutledge, and he's correct. CH4 is what you would write this as for the molecular formula. Now, you might also remember there was such a thing as a structural formula. Hopefully you will remember that because it's going to be on your test on Tuesday. It's representing what's up here. In other words, it's representing the bonds.
Oh, is that what, like, the lines?
That is correct. It is like with the lines. It would be the letter C, and then a line to an H, which represents this bond. Another one representing this bond, and so forth, and so on. And this is, as Sophie said very astutely, representing exactly the same thing. It's just, this is a little less complicated, a little easier to look at. It shows that carbon is forming a bond or sharing an electron. And as long as there are 4 lines, then everything's okay. That's sort of the basics of organic chemistry. I'll leave both of these up for right now in case people need to write. People need a minute to write. Take a minute to write. So yeah, let's catch up with ourselves and make sure everybody has that. Yeah, so Del.
Could it also bond with something that needed 3 electrons and then 1, like? Yes. Yeah.
Yes, it could. I'll tell you what. While people are writing that down, I'll write that over here. Tell you what. Sebastian, you can see in the screen there. Can you see in the
So
screen
they
on that?
bond with
Yeah.
How
nitrogen.
far over can I go before I'm off the screen?
Your arm's in the screen.
Yeah,
No,
yeah.
There.
Right there. Okay.
So they combine with nitrogen and hydrogen.
Right.
Then. So.
Yeah, and okay.
Or can it bond with itself?
It can bond with itself. Wow, I should pay you for those two questions because that's exactly where this goes next.
I'll take some money.
When I say pay you, I mean hypothetically. I don't have any money.
Oh.
I'm not allowed to carry. Driver is not allowed to carry cash. Because driver spends cash if he has cash. Okay. Yes. So take another minute to write that actually, and then we're going to go where Odell and Hayes said. Okay. I'm going to move on a little bit. So yes, carbon needs to make a total of 4 bonds. And depending on who it's bonding with, it can take care of those all at once or multiples at a time. What do I mean by that? Let's take a look at 3 other examples. So, okay, so first, how about, all right, nitrogen was one example we were given. And here's nitrogen, it's number 5? No, 7. I'm so sorry. It has 5 outer electrons. So if nitrogen has 5 outer electrons, we're not even going to show the inner ones now. How many more does it need?
3.
It needs 3. It has 5, needs 3.
My bad.
And so if it was going to bond with carbon, it could actually it could share all 3 of those with carbon. So here is what it would look like. That carbon can do all 3 of those bonds with nitrogen, and that's called a triple bond. And what you'd have is on the other side, you'd have to have 1 hydrogen or something else. You could have something else that only needs 1 bond on the other side. As long as, remember the rule is carbon needs 4. As long as carbon bonds to 4, makes 4 bonds, it can do that to almost anything, which is why carbon's so versatile. Because as we're going to see, carbon can bond to itself. I'll save that for last. But just to show you another thing, here's oxygen, which is number 8, and oxygen. I'm going to write OX for the little nucleus here. Here's the valence electrons of oxygen. 1, 2, 3, 4, 5, 6. How many more does oxygen need? 2. That is correct. And so oxygen can share 2 with carbon. So here's a carbon atom. And I'm so sorry, I'm going to have to erase the jellyfish. I like the jellyfish, but it's got to go. So this carbon can share, it can do one of 2 things. The oxygen can get two electrons from carbon, which then, I guess in theory, would have 2 other hydrogens attached to it. As long as carbon has 4, then it's fine. Oxygen's getting the 2 that it needs. The other thing, I'll do it in a different color, that the oxygen can do is that it can bond to an oxygen or a carbon on one side and a hydrogen on the other. Again, making sure everybody gets what they need. Oxygen needs 2, and so it's fine. But what's wrong with this picture? Carbon's not cool right now. Carbon needs to have its 4 bonds also, so I could do like that, and then everybody's happy. This is alcohol, actually, but we'll talk about why that is later on. Okay, so before people get too full, I'm going to give you the last piece of this little puzzle for right now, and then what we're going to do is we're going to play with some atomic models, molecular models. Okay, the last thing I'll say is that carbon can bond with itself. So in fact, I'm going to take over this space rather than right down here. I'm going to erase this and take over this space and show you what I mean. So for its last trick of the lecture, carbon is now going to bond with itself. And this is really where we get into why carbon is the versatile player that it is, and why carbon is the heart of living molecules, because it can make these simple small molecules. It can make CH4. I'll put up CH4 to start with, because you just saw that. CH4. But it can also bond with itself. I can replace one of these hydrogens with another carbon. And as long as this carbon also is bonded to 4 things, like maybe 4 other hydrogens, or 3 other hydrogens, excuse me, then that's fine. It's sort of like puzzle pieces. You can, if you have the right numbers, you can put anything together within reason. I could extend this, or you could do this. You could write below. Here's another one. I could make this go on for
polymers.
A whole bunch. Well, no, we're not there yet. Now, that's fine. What I'm showing you right now, this is a carbon skeleton. No, red doesn't work too well. How about blue? Blue's nice. This is a carbon skeleton. Carbon skeleton means that I can put carbons together as many ways as I can imagine, sort of, as long as each of the carbons has its 4 bonds. Now, they don't have them. It doesn't have them yet, but like, for example, I'm going to erase this to make myself a little room. I could put carbons going up this way if I want to, and then out this way. Doesn't matter. You can't stop me. I can do whatever I want. As long as I then go back and fill in what's supposed to be there. You don't have to do this. You can. It's in your book, shown like this. I'll show you in a second. If you just go back and fill in the H's, or I could do an O then an H here. As long as everybody has the proper number of bonds to achieve their desired number of outer electrons, then you can go on and on and on and make some ridiculously large molecules. I'll have to write these pretty small. And, well, what do we say? So again, this is the skeleton. The center part is the skeleton. So it's, when we say carbon skeleton, the carbon is really the framework. That's the way to think about this, folks. The carbon is the framework that all the rest of it gets built onto. And so it's these bonds from carbon to carbon that are forming what we call the carbon skeleton. And all the rest of it could be it could be anything, but as long as each of these has 4. If you look at any one atom, you see that it has 4. Now this carbon, I messed up on. It has 1, 2, 3 bonds to other carbons, but it needs to have a 4th. This carbon, 1 bond, and then 2 hydrogens. This one here in the middle doesn't have any hydrogens bonded to it, but it has 4 other carbons. And so they're all following the rules. So at this point, people's heads are starting to spin a little bit, so I will draw it to a close right there, and we'll play with some models and then see where we're at, and maybe we'll do another section of this lecture in a little bit. Okay? Thank you very much. I'm Mr. Arbach.